Okay, when we're swinging the buzzer around in a circle, now this goes back to the buzzer experiment, and if you haven't seen the video clip on that, you should go back and watch it. It's only a few minutes. But we're swinging the buzzer around on a string, and let's say we're swinging it around here and you're standing over here. Then when the buzzer comes up to the top of its cycle, it's going to be moving toward you at whatever velocity it has as it goes around the circle. When it comes down to the bottom, it's going to be moving away from you with whatever velocity it has as it goes around the circle. Now, in fact, the velocity at the top of the circle will be slightly less than the velocity at the bottom, but we're spinning it pretty fast, and there's not going to be that much difference. It'll be hard to measure. Okay, so let's assume that we have a buzzer at the end of a 1 meter string, so that we're spinning it around with a radius of 1 meter, and that we're spinning it around twice per second. Okay, frequency of 2 revolutions per second. Then the questions are, what's the velocity of the buzzer as it goes around the string? The velocity is going to be the product of the angular frequency, which is 2 revolutions per second, times the distance we travel per revolution. Okay, the distance around a 1 meter circle per revolution is 2 pi times the radius, which is 2 pi times 1 meter. So 2 revolutions per second, moving 2 pi meters per revolution, moves us at 4 pi meters per second, or about 12.6 meters per second. I'll note we could have also calculated this, and you should make note of this also, by saying that 2 revolutions per second is 4 pi radians per second. We multiply the 4 pi radians per second by the radius, 1 meter, and we get the angular velocity, or we get the velocity. Multiply the angular velocity in radians per second by the radius in meters. We get the velocity in meters per second. It's going to be 4 pi times 1, 4 pi meters per second, again, or 12.6 meters per second. You should understand the calculation both ways. Now we're going to make an approximation here. And it turns out that for small velocities, or velocities that are small with respect to the velocity of sound, these are pretty good approximations. Okay, we're going to say that the velocity of the sound is 340 meters per second, and the ratio of buzzer velocity to sound velocity is 12.6 meters per second over 340 meters per second, or about 0.037. So here's our ratio of sound velocity, of buzzer velocity to sound velocity. Now, if we assume that the sound waves bunch up in proportion to the ratio of their velocity to that of sound, and that's a fairly reasonable starting assumption for small velocities. Again, small velocity being something that's a lot smaller than the velocity of sound. 12 meters per second is about 30 miles an hour. It's not all that slow. But we'll then be able to say that the sound of the buzzer, and let's assume that the buzzer sound is around 3,000 hertz, which is fairly close. Okay, 3,000 hertz buzzer coming toward us will have a higher frequency. And if the frequency is 1 plus 0.037 times as great, that's going to give us a frequency of about 3,110 hertz. Whereas, if the buzzer is moving away, the frequency is going to decrease by this proportion and give us 2,890 hertz. Now again, this isn't a completely accurate version of what's going on, but for small velocities, we can actually treat it this way and make some pretty good estimates. Now let's see what really happens with the buzzer and compare it with the estimates that we've made. Okay, what we want to think about is in 1/100th of a second, if the buzzer's moving toward the observer, okay, in 1/100th of a second the buzzer's going to emit 30 cycles because it's emitting 3,000 cycles per second. The buzzer's also going to move 0.125 meters closer to the observer because it's moving at about 12.6 meters per second. The 5 really should be a 6 here, but it's not going to make a lot of difference. Okay, so the buzzer moves 0.125 meters closer to the observer. Okay? Now let's think about what happens. The buzzer is coming around the circle. Now it's here. In the next hundredth of a second it moves 0.125 meters, maybe to here, from here to here. Now the observer's over here. Okay? How long does it take the observer to hear the 30 cycles that the buzzer emits between here and here? The first of those cycles is emitted from this position and has to travel all the way from here to the observer. The last is emitted from this position, which is closer to the observer. That means that the 30 cycles are bunched up into less distance than they would be if the buzzer wasn't moving. Okay? The distance traveled by the last cycle is this much shorter than the distance traveled by the first cycle. Okay, well that means that the last cycle takes less time to get to the observer than the first cycle. Okay, how much less time? Well, 0.125 meters divided by the speed of sound. Okay, it's got this much less distance to travel at this velocity, so it's going to take this much time less to get to the observer. That means that the observer is going to hear the sounds in less time than it took the buzzer to emit them. So the observer will hear all 30 cycles in the 0.01 seconds less the difference in the time between the first and last cycles, or in 0.00963 seconds, so that the observer hears 30 cycles in this time, which gives him a frequency of about 3110 Hertz. Now that's right at the same estimate that we made by doing a percent difference. We can see the situation a little bit better if we symbolize it. We can understand it a little better. So we're going to come down here and we're going to do this with symbols. Okay, now let's assume that the observer is over here and the sound waves are emitted from the different points during some time delta t toward the observer. Okay? So, at clock time t, the source is at this point. At clock time t plus delta t, the source is at this point. The distance between these points is Vs delta t, where now I'm letting Vs stand for velocity of the source, because we're going to have to distinguish different velocities. Velocity of the source, velocity of the sound, and in a minute we'll consider velocity of the observer. So that over this distance, Vs delta t, we're going to have a certain number of cycles emitted. The number of cycles will, of course, be just the frequency f of the source times the time interval delta t. The number of cycles per second times the number of seconds. Now, in the time between the first and last cycle, sound is going to travel a distance the distance that the sound travels. Wait a minute. Now, let me say that again. Okay. In time delta t, the source travels distance Vs delta t, and the sound travels that distance, this distance here, in time Vs delta t divided by the velocity of sound, just distance divided by time. So that the sound takes this time to travel this distance. It means that the observer is then going to hear these f delta t cycles in this much less time than it took to emit the cycles. So we can make a statement like this: the observer hears f delta t cycles in time, what? Delta t, this is a cross out, ignore it, delta t minus Vs delta t over the velocity of sound. Okay, the sounds were emitted in time delta t, but they're going to be heard in this much less time. What do we conclude from that? We conclude that when the source of frequency f moves toward an observer at a velocity v, and we should call this Vs, then the observer hears the f delta t cycles in time delta t minus Vs delta t over velocity of sound time interval. The observed frequency is therefore going to be the number of cycles heard by the time in which they're heard. F delta t over delta t minus Vs delta t over velocity of the sound. So that the frequency, if we simplify this, dividing both sides, or numerator and denominator by delta t, is just going to be the frequency of the source over 1 minus the proportional velocities. Velocity of the source divided by the velocity of the sound.